All right, let's get right into it. Have you ever thought about the hidden world of digital conversations happening all around us? I mean, right now, inside your car or in a giant tractor out in a field, there's this secret, invisible language being spoken. It's what makes all our modern machines tick. Today, we're going to pull back the curtain and decode that language. I mean, just think about your car for a second. A modern vehicle has, 70, maybe even more, little computers called ECUs, or electronic control units. You've got one for the engine, one for the anti-lock brakes, the airbags, the power windows, the list goes on and on. So the big question is, how on earth do they all talk to each other perfectly in an instant? Well, before we get to the really elegant solution, you gotta understand just how massive the problem used to be. Back in the early days of car electronics, things were messy. And when I say messy, I mean just look at this. The old way was a literal spaghetti monster of wires. Every single function needed its own dedicated wire running from point A to point B. It was heavy, it was crazy expensive, and finding a problem? A total nightmare. Then came the new way, a clean, simple two-wire system, the CAN bus. And that brings us to the absolute hero of our story, the Controller Area Network, or as everyone calls it, the CAN bus. So what is this thing really? You can think of the CAN bus as the digital nervous system for a machine. It's kind of like a roundtable meeting. Every single ECU is sitting at the table. When one of them talks, say the brake sensor, everybody else hears the message. But here's the clever part. They're programmed to only pay attention and act on the messages that are actually meant for them.
So how does it stop being total chaos with everyone talking at once? Well, it has this brilliant system for prioritizing messages. See, every message gets an ID number, and the lower the number, the more important the message. So critical data, like you slamming on the brakes, is like an ambulance with its sirens on. It gets top priority and cuts through all the other traffic. No delays, ever.
And this system gave us three huge wins. First, it's simple and cheap. It got rid of miles of copper wiring, which cut down on weight, cost, and all the things that could go wrong. Second, it's centralized. A mechanic can plug into a single port and see what's happening across the entire vehicle. And third, it is incredibly tough. It's built to work perfectly, even in the noisy electrical environment of an engine bay. But, technology never stands still. As cars got smarter with things like advanced driver assistance systems, the good old CAN protocol started to hit a wall. The sheer amount of data flying around was just getting to be too much. So, we needed an upgrade. Enter CAN-FD, which stands for Flexible Data Rate. And the leap forward here was just massive. The original CAN could only send a tiny little packet of 8 bytes of data at a time. CAN-FD blows that up to 64 bytes. And while it keeps the same basic speed for compatibility, the actual data part of the message can be sent up to 5 times faster. Let that sink in for a second. That is an 8 times increase in how much information you can pack into a single message. That was a total game changer, especially for data-heavy stuff like modern safety systems. It cleared up all the network traffic and just made everything way more efficient. Okay, so here's where it gets really interesting. The CAN bus itself, the 2 wires, that's just the foundation. It's the physical network, but it doesn't actually define the language being spoken on it. For that, you need another layer on top. And different industries have built their own standard languages on this foundation. For big trucks and buses, that language is called J1939. In the world of boats and ships, they use something called NMEA 2000, which lets you plug a GPS from one brand into an engine from another, and it just works. And in farming, there's Isobus, which is how a John Deere tractor can perfectly control a sprayer made by a totally different company. I love this quote because it sums it up perfectly. Think of the CAN bus as the telephone system. It provides the physical connection, the dial tone. But protocols like J1939, they're the actual languages being spoken over the phone, whether that's English or Spanish or something else. They give the conversation its meaning. So we've got the network and we've got the language. But if you were to actually listen in on that network, you wouldn't hear words. You'd just see code. And that brings us to the final and maybe most important piece of the puzzle, translation. Because this is what raw CAN data actually looks like. You get an ID and a long string of what looks like gibberish. These are hexadecimal characters. To you and me, this is completely meaningless. It's like an encrypted message, and we don't have the key. So, how do we crack the code? We use this, a DBC file. It's basically a database for the CAN network. You can think of it as the Rosetta Stone or the official decoder ring for your machine. It's just a simple text file, but it holds all the rules we need to translate that gobbledygook into real, meaningful information. And the process is actually pretty straightforward. First, your software looks at the CAN ID and matches it to a set of rules in that DPC file. Then it knows exactly which bits inside that long string of data represent something specific, like engine speed. And finally, it applies a simple math formula from the file to turn that raw number into a real-world value we can actually understand. And voila! This is the magic. That raw, cryptic line of hex code from before is suddenly transformed into this beautiful, clean, human-readable table. We can see it plain as day. The engine speed is just over 1,500 RPM, and the vehicle's going about 86 kilometers per hour. We've gone from code to clarity. So, there you have it. We went from a tangled mess of wires to an elegant two-wire network. And then, we found the decoder ring that turns all that raw data into powerful, actionable insights. It makes you stop and think, doesn't it? With this hidden language flowing through practically every machine we use, what other secrets are just sitting there in the data, waiting to be unlocked?